Hello. Today's topic is about curve fitting and interpolation. Curve fitting is a way of an approximation. The technique uses a curve or a function to curve fit a data set. So the fitting could be precise or perfect. It could be good, very good. Could be poor, could be very poor. Of course, when we do curve fitting, we try to pursue the least error. While interpolation is another technique. It uses a curve or a function that curve fits all data points in the data set precisely. In other words, the curve will pass each point in the data set exactly. So today, you may say our topic is to use a single polynomial to interpolate a data set. Okay, we also know this. Is given that we have n distinct points, therefore we can use them to set up uniquely a polynomial of degree n minus 1. Okay, usually we have three approaches. We could use a standard form. Okay, this we may say is the general form, standard form. Okay, this involves calculations. Okay, to determine those coefficients through the data points. And we can also use Lagrange interpolating polynomials and Newton's interpolating polynomials. And it turns out Lagrange interpolating polynomials and Newton's interpolating polynomials are two of our best friends in the following chapters, especially Lagrange interpolating polynomials, because to set up such a polynomial, no calculation is needed. And the Newton's interpolating polynomials still need some calculation. Okay. Now, the fourth approach, using the standard form of a polynomial of degree n minus 1 this way. Okay, so this we have n distinct points, so that means x is known. Okay, it will assume the given values, and y is known. It's given in the data set. Okay, the unknown things are the coefficients. We have m coefficients to determine. We use the n given data points. We can set up such a system. Okay, it's linear. Okay, don't imagine, hey, the power could be large, could be just non-1 if it's, but they are constants. Okay, so it's this part that's unknown. So it's still a linear system. Say, for example, we want to find a polynomial which passes through these 3 points exactly. Okay, now we use each point. Say, from the first point we know when x is 0, y is 1, x is 0, a times 0 squared, b times 0 squared, 0 plus c. And now we use the second point. Well, x is 1, y is negative 1. y is x is 1. So a plus b plus c. Now, the third point, y x is 3, y is 1. X is 3, that's 9a. X is 3. So we have a system in 3 variables. C is 1. A plus b plus c is -1. 9a 3b plus c is 1. Yes, you just sum it for what? For a, b, c. Now c is fine. You put into this 2. We can change it to which one? A plus b is -2. 9a plus 3b is 0, right? And then you solve this 2, you can find a, b. So you can find a and b. Okay. So it must be, I believe y is x squared minus 3x plus 1. I believe it's this. Okay. So that's it. Okay. That's using the standard form of a polynomial of degree n-1. Now, Lagrange interpolating polynomials is this way. Okay, if we expand it, it's this. And we'll see how to set up this. Can you see something special here? You see, we have, okay, given data set is x, y. You have x1 is some value, y is some value, x some value, y some value, x some value, y some value. Okay, it's like this. You have a table like this. Okay, if this is x1, y1, okay, x2, y2, and so on. Okay, here, the first term will return y1, second term y2, last term ym. And that's an amazing construction of a function. Okay, I love Lagrange interpolating polynomials very much. Okay, and so how about the coefficient of y1, y2, ym? The denominators are always constant. You see, no variables appear in the denominator. Okay, just now you just see how about the coefficient. See, that's the first term. You may say, hey, corresponds to x1. The second term corresponds to x2. Last term corresponds to x sub m. Okay. Now, the numerator in each term. When this corresponds to x1, the numerator will not have x minus x1. No. X minus each other term, x values, and then find their product. No x1. Then second term, x minus each term except x2 itself. You don't have x2. No this. Okay. The same way you can construct all other terms, so that I said the last term is about xm. So in the numerator, you find x minus each term, each x except xm itself, and then find their product. That's numerator. Denominator. Okay, denominator is copy paste the numerator in each term and replace x with x1, x1, x1. You see, the second term the same way is about xm. You may say so. Okay, now the numerator, we copy the numerator to the denominator and then replace each x with x2, x2, x2. You see, change each x with x2 in the denominator. and so on. Okay, so that's the way how we construct a Lagrange interpolating polynomial. Why I say it's a cute, smart construction. You see, to calculate x1, y1, how about this? How about to verify if this works? Okay, how about this function at this y value at x is x1? We know it must be what? When x is x1, it will be y1, right? It will be y1. Really? You see this? When x, you evaluate at that point, x is x1, is x1, 0, x1. All other terms will have x1 in the numerator. So x minus x1, right? So each other terms will be 0. Only the first term survives. And it turns out you evaluate at x1, so they are the same, they cancel out. So yes, you get a y1. And same way you can say the second term, you evaluate y at x is x sub 2, you get y2, no problem. So why? You evaluated this polynomial at x is x sub 2, you replace x with x2, 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 yes, x2, 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 x2. Yes, you can see each other terms will have the x2 x sub 2 minus x sub 2. So they disappear. Only the second term, it doesn't have x2 sub 2 minus x sub 2. And now x sub 2, this cancel, this 2, they cancel out. Yes, you get it. Which one? y2. Only y2 could survive. Its coefficient is 1. So you can verify with all other points. That's why it's so smart a design or construction. Love it. I hope, I do wish this will be covered by every algebraic classes. If it's not so basic, it's for fun. Algebra, in some sense, is a special symbolical game, right? Okay, that's a game. Without calculation, we could set up a polynomial of degree n minus 1 quickly, easily, without any calculation. That's wonderful. It's because of this we love it. We should love it so much. Okay, now we'll see some examples. How about using data set? When, okay, x, y are given. Now you set up, for the first one we set up is this. We have this y1 times 52 plus y2 is 5. Okay, numerator. The first term is x minus any term x except itself. It's 1. You don't have this, so minus 2. And we only have 2 points, therefore that's just this. Okay. And the second term is x minus each x value except itself. So it's x minus 1 here. Now denominator, copy paste and numerator to the denominator. Okay, change x to x1. The second term, copy paste the numerator the same to the denominator. Now replace x with each x with x sub 2, x2, that's 2. Yes, that's it. Okay, and if you want to simplify it, that's negative 52 x minus 2 plus 5 x minus 1. Yes, That's it. Normally we don't want to simplify it, to expand complex terms. What's the point? Of course, you can say if you are supposed to find a linear equation, and you can do that, and because if you present such an answer, it will not be good. But in our cases, we want to differentiate it, integrate it. We don't have to expand complex terms. And in the following chapters, you'll see this. And possibly I'll give at least one more talk about things like that. Okay, if you want to simplify it, that's negative this. How many x? The negative 47x. Oh my, that's big. It's 104 minus 5, that's 99. Hopefully it's right. Okay. I mean, math professors normally are poor at mental calculation. Interesting. Okay. I was once very good at mental calculation before I saw a physical calculator after graduation from graduate school. And okay, now as the fourth one, and you can set up similarly. We can do this. Okay, let's try the second one. We have one more term. Yes, that's not good. And one more term. Which term? Y. No, it's this. This term, this one. Okay, y will be that. And negative 5, right? Okay, y value y1, y2, y3. Okay, now the first term, x numerator, x minus each x value, but it's solved. Okay, so it's x minus 2, x minus 4, and their product. The second term, again, is x minus each x value, but it's solved. X minus 1, x minus 4. Third term, x minus each term, but it's solved. Minus 1, x minus 2, right? Okay, numerator, denominator. Copy paste numerator to denominator and replace each x with x1. x1 as 1, 1. Same with the second term, copy paste numerator to denominator. Replace x with x2, that's 2, 2. Each term the same, copy paste, and replace x with x3, that's the third term. Okay, x3 is 4, 4. Yes, you have this. Okay, if you like, simplify it later. And this is, that's 3. 3 is 52 over 3, right? And x minus 2, x minus 4. Second term, that's negative 5 over 2, x minus 1, x minus 4. Last term, that's 3, 2, it's 6, x minus 1, x minus 2. Yes, that's it. So y will be like this. Okay. Okay. I don't want to complete the third one. Just follow that pattern. You can do it. Okay, just add one more term, one more term. Okay. And each time we need to redo the coefficients again. Okay, update each one. And then we cannot, when we set up a Lagrange interpolating polynomial for this dataset, though we know this dataset consists the subset, the dataset, it contains the subset, the dataset from of this first one, but we inherit nothing. We can use nothing from the from that one. Okay, same with this three, though. This dataset contains all points in the previous dataset, but we needed to redo the work. We cannot. Nothing is common between the two except the procedure, the method. Okay, so that's something bad. And the Newton's interpolating polynomial will get rid of this, will overcome such a disadvantage. And we'll see later. Now, how about find the interpolated value at this point? That means to evaluate this function polynomial at x is 1.6. This is horrible. I don't want to do it. Okay, and you just have patience. You replace to evaluate at this. You just do this. Replace evaluate. Oh my, evaluate. That's a lot of work to do. Okay. So have patience using your calculator, and when you do your assignments, take an exam, you may use MATLAB, LUO plus Mathly to help you do. Okay. LUO plus Mathly provides a Lagrange function. Okay, interpolating polynomial, it gives you. Okay, that's this. Now, as you can see from the evaluation, from the construction, you can tell something. Okay, data points here in this way to construct a polynomial, the data points don't have to be evenly spaced. That's good. Okay, so and actually in the following chapters, normally we always assume data points are evenly spaced. Therefore, if this is negative h, negative 2h, and so on, and we can do more. Yes, well, anyway, it's good for us to derive formulas for differentiation, for integration, and so on. Now that's a good thing, and the best thing is that it's so easy to set up. No calculation is needed at all. Okay, bad thing, as you can see, when you want to evaluate a value, say like in the previous example, we evaluate x at which one? 1.6. And now you need to do 1.6 minus each one, 1.6 minus, oh my. And the evaluation, the calculation is over the entire data set. Each term. You have n minus 1 subtraction and n minus 2 products to find the products. That's each term. And not mentioned, you must have a denominator because all x values here, they are known. So you can, when we evaluate at many points, it's fine. You can set up this first. So okay, it's the numerator. So the calculation is over the entire data set. So in that case, the time performance will be poor, very poor. Okay, especially compared to polynomial in general form, in the standard form. Okay, so, but I don't believe this is some disadvantage, because who will put such a thing into their product? So no, this just gives us great convenience while we derive formulas. Okay, for integration, for differentiation, for solving yes, differential equations and so on. Okay, so that disadvantage is disadvantage, but who cares? As I said, we don't put it into use in our product. That's normally the case. Okay, now that's a bad thing. Not easy to expand. If you want to expand your data set, you collect more data to put into the original data set. Now you need to rework. Okay, and the working with the previous data set doesn't help at all. Okay, if you say disadvantage, that's really one disadvantage. Okay, now Newton's interpolating polynomial is this way you construct it. Again, it's a small, cute construction. Why? This way, and as you can see, the fourth term is just constant. Second term, you have this. Third term, you see, it contains this term, right? This part, right? Factor. And this third term, it contains this part here. Okay. In this case, we still have, if we have n data points, the polynomial will have which one? Eventually, you will have, finally, it's a m. Here you have x minus x1, x minus x2, x minus x, and no, sub m minus 1. Okay, so that term, if you expand it virtually, just imagine you have x to m minus 1 plus something, right? Yes, that's the that term determines, it says, okay, here this polynomial is of degree n minus 1. Okay, now we have n coefficients to determine. A sub 1, sub 2, sub 4, sub m. Okay, and how to find that? And what's the difference from which one? The general form, the standard form? We'll see. It turns out, again, this one, in some sense, is better than that one, the general form. Say, for example, you find this. Okay, to find, in this case, we know y will be a1 plus a1 x minus x1, right? Yes, that's the first term for the first data set. Now a sub 2 method. To find a sub 1, a sub 2, we use the 2 points to evaluate. When x is 1, y we evaluated at x is 1, x1. Now we know the value is what? We know the value is 52. And here you have x1 is 1 here. x1 is 1 here. Yes, now x1 this term disappears, right? So it's 0. So that's just a1. So a1 is always which one? y1. y1, y1. Okay, now a1. So therefore now a1 is 52. You can find now to determine a2. Now evaluate at x sub 2, while at x is 2. We know that y value is 5. Okay, here as 52 plus x is 2 minus y, it's a2. Okay, so a2 is negative 47. So therefore, that's negative 47. That's the Newton's interpolating polynomial. Okay, for the given data set. And usually we don't want to expand this and combine like terms. But if you want, this will not be true. We assume you forgot the way to set up the tangent line, or to set up the equation of a line passing through 2 points. Now you use this technique, you will not present this as the final answer, because people will will laugh. Okay, my goodness, what's this? And you will have to expand and combine like terms. It's negative 47, and oh my, that's 99 x. Okay, so why will be this? That's the fourth one. Okay, now we'll see how about the second one. With the second one, we set up y as a1 plus a2 x minus x1 plus a sub 3 x minus x1 x minus x2. Yes, set up this way. And how about a1? You evaluated this at y at x is 1. Now when x is 1, it's 52. It's 52. And a1. Each turn you have 1 minus 1, 1 minus 1. So it's just a1. So a1, okay, is 52. No problem. And now evaluate. Now this is known. It's 52. Now evaluate that y at x is x2. That's 2. And we know y is 5. So 52 plus x is 2. That's a2. And this you have 2 minus 2. Yes, so it's just this. So you have a2 is negative 47. Now how about so this is negative 47. And now evaluate at the last point, 4. X is 4. We know y's value is negative 5. And so it's 52 minus 47 here. 4 minus 1 is 3. And this term is how much? This x is 4. 4 minus 1 is 3. 4 minus this is 2. That's 6. You have 6 a sub 3. Now in that equation, a sub 3 is the unknown. Only unknown. You solve for this, you get this 14 eventually. 14. Okay. So we have found this. Okay. We have found this finally. Okay. So as you see, now you compare the two data sets. Data set 2 contains data set 1, right? Or in other words, data set 1 is a subset of data set 2. Okay, in this case, you see how you compare these two. Wow, they are exact. The first two terms for question 2 is exactly the same as, yes, the terms for which one? For data set 1. And therefore, as you may be, yes, brave enough to predict how about for this third case. It contains data set 2 as its subset. Okay, in that case, they are exactly the same. So in this case, y will be 52 minus 47x minus 1, 14, x minus 1, x minus 2, plus one more term is negative 6, x minus 1, minus 2, minus 4. Yes. Okay, so they are exactly the same. Okay, so that's the goodness of Newton's, or the advantage of Newton's interpolating polynomials. Data set could be expanded. If we expand the data set from the original one, now the working for the original data set could be reused. We just add one more term. Okay, just add extra terms if necessary. Okay, so and then to evaluate the function's value at x at 1.6. Okay, say for example is this case, given that we have this. Oh, that's for the second one. For the second one. Okay, given that we have all this. Okay, so to evaluate it, we just replace each x in the function with which one? With the value. With the value 1.6. It's a 1.6, 1.6, 1.6. Oh, yes. So the more terms we have, the more points we have. Yes. Each term, on average, you're doing more work, right? Yes. The last term will involve how many? You find the difference. Do subtraction. How many subtractions? n minus 1. And find the product. That many products. Find the product. That many multiplications. Okay. So the time performance is better than Lagrange interpolating polynomial because here we don't have that many, right? Yes, for the first terms. Anyway, but when we evaluate the time performance of an algorithm, we always consider the worst case. The worst case here, the last term involves more work, right? We use this to count. Okay, so but as with the Lagrange interpolating polynomials, actually, who will put this into the final product? Again, Newton's interpolating polynomials and Lagrange interpolating polynomials, they are the same. In that sense, we just use them to derive formulas. It's for us, for human beings, we derive formulas through them. And okay, and not like with in Lagrange interpolating polynomial, Newton's interpolating polynomials have special way, yes, algorithms for us to find all the coefficients a1, a2, a sub 3, a sub 4, those how to find them. And imagine, okay, always imagine you have such a table. You find the divided difference, and divided difference, and their divided difference. Oh my. Okay. And if you are interested in this, you look. You can Google. You can read your book. Okay. And it's interesting topic if you want to do something. Okay. And I don't want you to remember things like this. It's not interesting. Okay. Okay. So I implemented the code years ago. The algorithm, yes, that's my lab code. How to find the coefficients for? Oh, that's not. That's Newton. I'm sorry, Newton's. Okay, Newton's interpolating polynomial. I just copy paste. My fault. Okay, use the that's a recursive implementation, and you can have recursive algorithm. Normally, the time performance is poor than non-recursive one. Okay, now you see it's so short. Okay, if you are interested, you can check the code. Okay, that's this. And now that's Newton's interpolating polynomials. Yes, its advantages, disadvantages. Again, like with Lagrange interpolating polynomial, data points don't have to be evenly spaced. And though, again, we tend to, when we derive formulas later, we normally, in most cases, we assume data points are evenly spaced. That will give us even better thing. Okay, and that's good thing. Okay, if you have a you have worked out a Newton interpolating polynomial for a data set. Now, if we expand your data set, you can just, you don't have to rework all things from scratch. You just borrow the work for the original data set and you just add more terms to it. Okay, that's good. And okay, better thing is this. The calculation, if you evaluate the worst case, that's this. The calculation, if you want to evaluate such a polynomial at a given point, therefore the calculation is over the whole data set. So time performance is poor. Again, I said don't worry. Okay, because we just use it to derive formulas. We don't put it to real product. Okay, now it's easy to set up. Okay, and